exactly what we said over here.
For where the part that you said excludes the convolution, this is just computing one dot on that image. It also has a bigger summation that is based on the size of the image.
No, it's the full convolution.
Well,
So this will be, so to answer your question, ij in this example will be 1 through 8. So because our answer is an 8 by 8 over here. If you take a look over here, this is an 8 by 8. Okay. In the previous example, this ij will vary from 1 through 24. Okay. Okay, so anyway, hopefully this equation is important to us. So if there's still a confusion, let me know, because in the back propagation, we'll be taking the derivative of this particular equation. Okay. Anyway, so now rest is easy. Once we go pooling, you can just further, just like I did the pooling over here, Cp of m. The only difference is now what will it operate on? Instead of Cn, it will operate on Cn of 2, right? Otherwise, this is the same. So, as far as the forward pass is concerned, it's just by programming these equations, we can easily come up to all the 16 values, right? Then the last part is simply converting them into, so this is usually called the flattening. So we basically flatten all the 4x4 results over here into a single 96 by 1 vector. And then rest of it is like a regular network. Right? Now, let's talk about the backpropagation. Please see. Okay. Yes?
Is the bias inside the outer summation? Or it's like after we complete the convolutions, we add the bias?
We add a single bias to all the convolutions. So it is after the convolution. Okay. So if we have 6 feature maps over here, there's single value being added to the entire, just like we did it over here, a single value to all the 24 by 24 values. Okay. Okay, now sometimes when we create CNN networks, as we are doing the backpropagation, right? Obviously, we have to optimize the parameters of our model. So you should be able to easily see how many parameters we are going to optimize. So let's count the number of parameters that we have to compute the gradients for. Okay, so let's start from the output side, right? Each one of them you will see will have a single bias. You guys agree? So B1, B10, whatever. This one will have 30 biases because each neuron has a separate bias. Okay, so starting from the output layer, we have 10 biases, correct? Plus, then we have to learn the weights, right? How many weights? 10 by 30, 300. So this is basically W2. Okay, then how many biases in this particular layer? 30. So 30 biases. Okay, plus then we further go and okay, 30 by 96, W1. Okay, then let's go backwards. Okay, so what are the parameters that we need to learn over here? How many biases over here in this part? 6 biases. Okay, plus. Okay, we also have to learn the kernels. As you will see, the kernels are initialized randomly. The 5 by 5 matrix will be initialized randomly. So now, how many in this particular case?
24.
5 times 24. So this is basically the kernel in the second layer. Okay, and then if we move backwards from here, then basically we have more kernels over here. And how many kernels are there? So what it
It's
is?
about 5 by 5 by 24.
5 by 5 by 24. Okay, so then we will have 5 by 5 times 4, because we have 4 kernels in the first layer. Okay, plus, how many biases in the first layer? 4 biases. Okay, so that is the number of parameters that our system will be learning. Or those are the parameters we have to optimize via training. Right? Okay, so now let's take a look at the backpropagation algorithm. In the backpropagation algorithm, let me leave this equation because this is important. So let me go 5-10 more minutes, then I'll give you a break. Okay, let me remove this also, that's easy. Okay, we'll leave this. Okay, so let's start from the delta over here. Okay, suppose you were doing softmax with cross entropy, right? So then do you remember the delta in the last layer is pretty easy? Okay, what was the delta in the last layer?
A minus y.
Was it A minus Y or A minus S? I thought S was the output of the. Okay, so you can double check that. I thought it was A minus S, but. So anyway, we know the delta in the last layer. Obviously, if we are using mean square error, for the mean square error, this was, no, I think it was Y minus.
Yeah,
A minus Y was the error? Okay, you were right. A minus Y. Okay, so anyway, once we have the delta in the last layer, right? Then this is easy. For example, what will be partial L over partial W2? Okay, so wouldn't that be partial L over partial A2 times partial A2 over partial W2, right? And if this is A minus Y, then further A2 over W2. So remember, this is basically what's the inside over here. There's a sum over here.
But the output is A1, so it's going to be A1.
A2 over W2. So if you rewrite the equation for A2, isn't the equation for A2, let me write it over here, A1 W2 plus B, whatever that B is, right? Because A1 is acting as the input over here. So if I did the partial with respect to W2, it will be simply A1.
Yep.
Okay, then if we further multiply it with the derivative of the activation function, so if we further multiply, let's pretend over here it's the sigmoid. So wouldn't that be A1, 1 minus A1? So assuming sigmoid. And so this will be delta in previous layer. You guys agree? Okay, which is basically, this is delta in last layer times the,
Activation derivative.
I'm missing the W, sorry, I'm missing the W somewhere over here. Okay, let me backtrack. Over here. Okay, this was partial L over partial W2 was up to over here, correct?
It's partial into over partial S2 and then partial S2 over partial.
Okay, so now if we go to the delta in this particular layer, which will be
Output of previous layer into delta.
partial L over, yeah, so up to the delta over here, if you remember, gets multiplied by
The weight matrix.
the weight transpose or something like this, right?
Yep.
So anyway, so delta in hidden layer equal to
The W2 into output of,
delta in last layer
into output of the previous layer.
multiplied by
T1.
the W2. Okay, now depending on how we organize it, the transpose or, so I won't worry about the dimensions over here once we implement it, what type of batch code we write. There may be a transpose, there may not be a transpose, but anyway, as long as we make sure the dimensions are working fine. Okay, so then this further will be multiplied by activation function over here, which will be A11 minus A1. Right? Everybody agrees? So we know the delta up to this point, right? Okay, so then if we project it further backwards, what do we have to do to this delta to get the delta over here?
Multiply by the weight matrix and the activation.
Okay, there is no activation
So
over
one,
here.
so one, right?
So this will be basically delta in hidden layer multiplied by
W1.
W1, and again there might be a transpose,
Yeah, that's it.
so this will be delta over here. You guys agree?
Yes.
Okay, so once we have computed the deltas in the flattening layer, okay, so then what will we do? How many values will we get over here for this delta?
96.
96 values, right? So then what we need to do is we need to compute the deltas over here. Deltas over here. So that's easy. All we have to do is
This delta.
the first four values will go become the first four values. The next four will become, so basically we do the reverse flattening now. Okay, so we know the deltas here, which essentially are the same as the deltas over here, no difference. The only difference is here they are in linear fashion, here they are in a 4x4 type of fashion, right? Okay, now let's go backwards. So how is this delta related to this delta? Okay, see here we were doing a pooling, right? For example, once we do average pooling, what do? We basically take four values, then what do?
Calculate value.
Divide by 4, right? So think of this way, as if we did x plus x plus x plus x plus divided by 4. If I did a partial partial by partial x, so let's make it x1, x2, x3, x4. Anyway, partial by partial x case. So basically what happens is here, this delta is essentially 1/4 of the delta over here. Okay.
Yeah.
So it's sort of like this when we do like 1/4 x, pretend x is the sum of all of these. Okay. So then if I do partial x over, or partial by partial x, we get the answer 1/4.
If that matrix was 8 cross 8, then the delta would be 1/8?
No, it doesn't. It has nothing to do with the size of the matrix because the operation was add 4 values, divide by 4. It was pooling on the 4 neighbors.
4 neighbors.
So if moving forward, it was dividing by 4, right? By adding these values. So then once we go the reverse delta, we also divide this delta by 4.
Okay.
So anyway, each one of these values, as you can see, will be divide by 4 from whatever we had the delta values over here. Okay, so that's straightforward, right? So if we have the deltas in this layer, what will be the deltas over here then?
This delta multiplied by the
Derivative of the activation?
Yeah.
So whatever that output is, in the forward pass, if we had stored that output, okay, suppose that output is called Z, then what will this be?
so z times 1 minus z into the
Z times 1 minus Z if it's a sigmoid, right? So do we know this delta?
Yeah. Yes.
Okay, so now comes the complicated part. So once again, knowing the delta up to this point is piece of cake. Okay, really, there's nothing special that we did. Okay, propagating the deltas back here, here, here. This got, the reverse flattening occurred over here. Here we simply multiplied each one by 1/4. Here we multiplied by the derivative of the activation function. So these deltas up to here are perfect. Okay, so the last, the complicated part is now, how do we go further and compute? There's a couple of things we have to do. We have to compute the derivative of the loss with respect to the kernels so that we can adjust the kernels. Then we have to further go and translate this to some delta over here, then delta over here, then delta over here, and onwards. Okay, so let me give you a break so that you guys are completely fresh and we can focus on the complicated part after the break.